Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all in class of Elementary Number Theory by David M. Burton. My name is Azmat Ali. Our discussion is continue on chapter number 8, primitive root and indices. Lastly, we discussed theorem 8.4. In today's lecture, we will discuss a corollary of this theorem, and this is very important result of this chapter. Actually, by using this corollary, we can evaluate how many primitive roots of an integer exist. This corollary says, if suppose n is any positive integer and there exists at least one primitive root, then total number of primitive root for this integer n are given by the formula phi of n. And actually this result I have already been used in my previous lecture. You can watch my lecture whose title is how many primitive root of n is equal to 50 does exist. We can again repeat this formula here. Suppose I take n is equal to 7. Then I know one of the primitive root for n is equal to 7 is 3. So my a is 3 here. Now, if we apply this formula on n is equal to 7, when it is confirmed that one of the primitive root exists here. So total primitive root are simply given by phi of 7. Here phi is Euler Totient function. So firstly we calculate what is the value of phi of 7. Phi of 7. As 7 is a prime number, so at any prime p, the value of phi is simply given by p minus 1. So this is equal to 7 minus 1 here, which is equal to 6. So it means now we have to calculate phi of 6 here. By putting phi of 7 here, this becomes phi of 6. If we make prime factorization of 6, this is simply 2 into 3. We know phi is a multiplicative function. Mean to say we can apply separately phi in the form of product at both of these integers. So this becomes phi of 2 into phi of 3. Again 2 and 3 are prime integers. So again we can use this formula p minus 1. This becomes 2 minus 1 into 3 minus 1. 2 minus 1 is 1 and 3 minus 1 is 2. This is equal to 2. It means there are total 2 primitive root for n is equal to 7 here. So this is the concept of this formula. This formula is used when we have already known that there exists at least one primitive root. Then total number of primitive root for this formula will be phi of n. Next we prove this formula with very simple steps. In last lecture, we discussed theorem 8.4, whose statement is, in a simple words, theorem 8.4 says, if a is a primitive root of n, then its powers generate all integers co-prime to n modulo n. This theorem simply says, if a is a primitive root of n, then all power of a raised to power 1, a raised to power 2, a raised to power 3, up to so on, last power will be a phi of n. These all power will also co-prime to n. Co-prime mean their GCD with n is equal to 1. Two numbers a and n are called co-prime or relatively prime if their GCD is equal to 1. So this is the theorem 8.4. Next, we prove its corollary. If n has a primitive root, then it has exactly phi of n of them. Mean to say total number of primitive root are phi of n. Suppose a is a primitive root of n. Suppose one of the primitive root of n is a. By above theorem, any other primitive root of n is found among the number of the set. You can notice that the elements of this set are actually the power of A, and above theorem says all the power of A are relatively prime to n. These numbers are power of A, and above theorem says all the power of A are relatively prime to n. Here star represent, this is an important step that I will explain here. This is not any other mark or identity. Explanation of this star. For an integer a to be a primitive root of n modulo n, the first condition is that a should be a relatively prime to n. This is the first condition for an integer to be a primitive root, that it should be relatively prime to n. As the set of numbers, this set of number are all relatively prime to n according to theorem 8.4. These are all relatively prime to n. If these numbers are also relatively prime to n, and according to first condition of primitive root is that that number should be relatively prime. It means, so existence of primitive root is possible among these numbers. So other primitive root must exist among these numbers, from these numbers. So it means your other primitive root belong to this set. Next we calculate how many number of such primitive root exist. These are the power of A. Next, this is the important line that I am going to write here. Only those powers of A will be primitive roots of n. Only those power of A, suppose these power are denoted by k, will be primitive root of n whose GCD with phi of n is 1. So now I have to calculate, now I have to count all those powers whose GCD, the power are denoted by k, so whose GCD with phi of n should be equal to 1 here. Now I have to calculate all those k, how many such k exist which are relatively prime to phi of n. This is my target. But the number of power a raised to power k, where k lies between 1 to phi of n, because the first power of any integer is a raised to power 1, this is equal to a. The second power is a square. The last power is phi of n in this set. So that's why I have written here your k lies between 1 to phi of n, because the total power are starting from 1 to last power is phi of n. But the number of powers that have order phi of n is equal to number of integers k for which GCD of k and phi of n is equal to 1. Here, why I have written here whose order is phi of n. Actually, this is the this is the primary definition of order of an integer, primitive root. Sorry, we say an integer a is primitive root if its order is phi of n. When its order is phi of n, mean to say a raised to power phi of n is congruent to 1. Then we say that a has order phi of n, and it is the primitive root. So when an integer has order phi of n, it means that is a primitive root. So but the number of powers that have order phi of n is equal to number of integers k for which their GCD is equal to 1, and these are calculated by this formula phi of n. Such integers, hence phi of n primitive root exists. Next below here I am explaining the step double star. Why we are explicitly count the number of such integer by using this formula. Why we are strictly count the number of integer by this formula here? Actually, what does phi of n represent? It represents number of all those integer which are less than n and which are relatively prime to n. This is the Euler-Totient function, and it represents all those integers which are less than n and relatively prime to n. Similarly, phi of n shows number of all those integer which will be less than phi of n and which are relatively prime to phi of n. Here we will write phi of n. So when we say some integer k satisfy this equation GCD of k of phi of n is equal to 1, so their counting is given by phi of n. There is no other formula that can count all those integers which are relatively prime to k. These are just calculated by the Euler-Totient function. So when you write GCD of k into n equal to 1, then total numbers are given by phi of n here, because here is n. But when you write GCD of k and phi of n is also equal to 1, then the total number of k are given by phi of, what is here? This is phi of n. So I hope this is very simple concept, and now you have a clear understanding of this discussion. So if you find this lecture helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.